Vivek Iyer. I'm a software engineer at LinkedIn.
Hi, I'm Goja. I'm from LinkedIn as well.
So today we are going to talk about how we at LinkedIn helped strengthen Pinot's query processing engine. And we did that with two features. One is adaptive server selection and query killing. So this talk is going to be divided into two main sections. The first part, I'll be covering the adaptive server selection. And in the second part, Ja here will be covering the query killing side of things. Okay, so let's dive in, right? So for adaptive server selection, the agenda is going to look as follows. So we will start off with the problem that we are trying to solve here and why it is important. Then we'll dive deep into the design decisions and how we solve the problem, followed by some benchmarking numbers that we obtained before we deployed it in our production environment. And then we'll follow that up with the results achieved after we rolled it out to our entire production environment, right? So before we jump into the problem statement, let me briefly set up some context about how Pinot processes queries. So there are two main components involved in Pinot's query processing. One is the Pinot Broker and the other is the Pinot Server. So the Pinot Server hosts the actual data and that the tables contain, and it hosts it in the form of segments, right? And Pinot Broker is the component that receives an incoming query and it routes it to these servers in order to process the query. And each segment that we are talking about here is hosted by multiple Pinot servers, and the number of replicas is governed by something we call a replica group or a replication factor that you can set dynamically in the table config, right? So when a Pinot Broker receives a query, what it is going to do is it is going to pick one of these replicas in order to route the query to, and the algorithm that it uses today is a very naive round robin approach, and we have it that way to keep it as lightweight as possible. But therein lies the actual problem that we are trying to solve here. So the issue with round robin is, as we know with any distributed system, we are going to use a bunch of commodity hardware, and all these hardwares are susceptible to slowness issues, failure issues. Personally, at LinkedIn, we've seen a number of cases where the servers slow down because of things like long GC pauses, network issues, disk failures, and so on. And with round robin approach, what happens is it is not cognizant of the fact of how these servers are behaving. Whether the server be slow or fast, it's still going to route equal number of queries to the Pinot servers, right? So what we need here is a more intelligent approach for query routing at the Pinot Broker so that it can be cognizant of how the servers are behaving, thereby achieving good results, right? And the magnitude of the problem multiplies several fold when we operate Pinot at LinkedIn scale. So at LinkedIn, we have about 5,000 plus Pinot server hosts and about 1,400 plus Pinot Broker hosts that are processing about 250,000 queries per second across 4,500 Pinot tables. So if we work at this scale, we try to quantify the pain points that we have at LinkedIn, and we saw that the Pinot team at LinkedIn spends about 72 plus engineering hours trying to triage these slowness issues whenever latencies shoot up, and our customers see that there is a availability degradation whenever the servers become slow. And we also have breaches to latency SLAs that we've promised to our customers. When the servers become slow, we have about 30 plus events per quarter. And whenever we triage these issues, there's an elevated sense of urgency because we are all dealing with production use cases here, and it leads to escalations and so on. So now that we have the problem statement set up, let's dive into how we solved it at LinkedIn and for the open source community. So the design for this feature consists of two major components. The first component that we are going to talk about is called the stats collector. So the stats collector is basically a stats store that is going to maintain stats about how each server is performing. And this stats store is local to each broker, and it is all kept in memory. We made this decision very consciously because there is a high cost involved with exchanging stats across brokers, and there is also a lot of code complexity involved. And in a lot of cases, Pinot is serving really high QPS use cases. So by the time the other broker receives these stats, the stats could be stale. So the stats collector stores several stats today. As of now, the current open source implementation collects stats regarding how many ongoing queries a server is processing, what are the latency results seen for each query. The other important component that we are going to talk about here for this feature is called the server selector. The server selector is nothing but a collection of server routing policies that we've built in, which is going to consult with the stats collector to make a good decision. So given a set of server candidates, it is going to apply these algorithms that are baked in and pick the best server. These decisions are again local at each broker. The brokers do not coordinate between themselves to make a decision. So it's important to build a routing algorithm that is good enough to work independently on each node. And again, in our open source implementation, we already have provided support for a bunch of server selection policies. We have about 3 policies now. The first policy is purely based on the number of in-flight queries that a server is processing. So it's pretty naive. What it does is it routes the query to the server that has the least number of ongoing queries. The second policy that we have is based on latencies. It routes the query to the server that is seeing the lowest latency times. The third policy, which we will be covering in our slides to come, is basically more sophisticated. It tries to use both this number of in-flight requests, the latencies. It also has some heuristics baked in, and that is the policy that we will cover in more detail, and that's the one we have deployed in LinkedIn as well. And these two components help the Pinot Broker become much smarter and route queries in a better fashion. So the workflow basically looks like this. So we have a Pinot Broker. This is a naive round-robin based Pinot Broker that is going to route queries to each of these Pinot servers. And here we have 3 Pinot servers, S1, S2, and S3, that are all hosting the same segments. We are going to replace this with a sophisticated Pinot Broker that has adaptive server selection feature. And we can see these 2 components that we talked about, the server selector and the stats collector. So when a query Q1 initially comes in, the server selector is going to consult with the stats collector. The stats collector in this case is not completely warmed up with all the stats for all the servers. So initially, the routing is going to be based on the older round-robin approach until the stats collector is completely warmed up, right? So initially, when Q1 comes in, the selection of the server is going to be random, so we pick server S1. The same happens when Q2 comes in, the same happens when Q3 comes in, and finally when query Q4 comes in. Now the broker has enough information about each and every server in the system, so all subsequent queries that come in will be routed by the server selector using one of the algorithms that we've seen, right? So the stats collector and the server selector that we see here is in the critical query processing path. So any sort of heavy lifting or computation that we do here is directly going to reflect as elevated latencies for our customers. So it's very critical that this is as lightweight as possible. That's the reason that's the reason we have stats collector as an async thread that runs and does this processing rather than having it in the same thread that processes the query. And one more thing is the stats collector is easily extensible and pluggable. That basically means that if you want to add more stats to for your routing, for your use case, or want to tweak the policy or write a completely new policy, it can all be easily done. And the stats collector basically collects stats at 2 important places during query processing today. The first one is before the query is dispatched to the server. It updates stats about how many queries the server is processing. And the second point where it's updated is when the results are received from the server for a query. At that point, we update stats regarding the latency and the QPS again. So moving on. So when we wanted to build our server selection policy, we wanted to tick a lot of checkboxes because we wanted a generic server selection policy that works well for the varied use cases that we have at LinkedIn. Particularly at LinkedIn, we have low QPS, high QPS, low latency, high latency use case. We did not want to be in the business where we tweak this logic for each and every use case and have an operational nightmare. So we wanted the server selection policy to be as lightweight as possible. We wanted it to be able to quickly detect when a server becomes slow and dial down the QPS appropriately for that server. And at the same time, when a server that has gone slow has come back and become normal, we want to be able to immediately dial up the QPS that we send to that server so that we are optimally using all the resources in the system. And the other main point that we wanted to prevent is herd behaviors. We wanted the algorithm to be very well behaved because each broker is making this decision locally, and there could very well be a possibility that all the brokers identify one particular server to be really strong and performing well. So all these brokers now send the queries to a particular server and then bring it down. So we wanted our algorithm to make sure that herd behaviors don't happen. And that is where we built an algorithm called the hybrid server selector algorithm. So this was, on the surface it looks pretty simple. All we are going to do is we are going to rank all the servers in the system based on a particular formula that we see on the screen here. And then when a query comes in, we are going to pick the server which has the best score. So let me break this formula down a little bit for you folks here. So what we have here is a cross product of the estimated queue size raised to an exponential power of n and the latency, right? So let's talk about the latency a little bit here. So what the broker is collecting is basically the latency values it sees for each and every query that comes in. And the latency we have here is an exponential weighted moving average with forward exponential decay. And what I mean here is when we compute these latencies, we give a higher weightage for the latencies values seen in the recent past than the latency values seen much earlier. The reason is we want to make decisions based on how each server is behaving in the last 5 to 10 minutes rather than making these decisions based on how the server is behaving 1 hour back, right? Because things could have gone down south in the last 5 minutes. And the other thing is for the estimated queue, it is nothing but a summation of the raw value of the total number of in-flight requests that a server is processing. And here is where we have a heuristic built in, which also accounts for how much load the server might receive in the near future. So the reason for having this heuristic built in is twofold. One, we want to avoid herd behaviors. So we do that by trying to forecast how much load a server is going to receive in the near future. And we also want to account for some sort of concurrency compensation because this server that we are routing to is also going to receive requests from the other brokers. And if you see here, the estimated queue alone is raised to an exponential power of n. The reason for doing that is we saw that we wanted our server selection policy to have two main traits. One is auto recovery and quick detection. And we saw that if we raise it to an exponential power of n, the algorithm quickly reacts to changes on a server, be it dialing down the QPS or dialing up the QPS when an event occurs on the server. And this algorithm, actually a lot of research went into building this algorithm, and we took ideas from how Cassandra does it, particularly using the C3 algorithm, and it is heavily influenced by that algorithm here. So all of these parameters that you see here for exponential weighted moving average, the exponential function n, are all tunable. You can all do that you can all set it per host at the broker level. And what we observed is this algorithm is pretty stable and you don't need a lot of tuning on a per use case basis. So based on our personal experience at LinkedIn, what we see is we just have one set of values that we use across all our use cases at LinkedIn, and it's been performing really well for us at such a large scale. So now that we've seen the design for the system, let's move on to the regression benchmarking. So obviously one of the questions we have is, okay, this algorithm behaves well when a server goes down south, but in an ideal condition where servers are all performing well, what sort of overhead is added into our query processing logic? So that's the reason we measured how much overhead is added to the query routing phase. So this is the phase where the broker decides which server to route a query to. And we see that before we had this algorithm in place, we saw some latencies in the order of 0.01, 0.02 milliseconds. And when we brought this algorithm into the system, the overhead is not much. it is in the order of 0.01 to 0.02 milliseconds in extra. But the good thing is, when we observe the total query processing time, that is the total time taken from when that query is received till the results are given back to the user, we did observe that the total time came down a tad bit. And this can be clarified by the fact that even though we take a little more time during the query routing phase, it is kind of compensated because we pick the best server to process the query, and so the results come back sooner. And we actually tried this experiment for varied QPS. So at 500 QPS, we do see that with adaptive server selection, the results are a little faster than without. The same results can be seen at 1000 QPS, and this is all 1000 QPS per broker. And when we even stretch the broker thin at 1500 QPS, we did see that the algorithm performed better, particularly at the tail 99 and the 98 percentile. So this is the regression benchmarking that covers how the system behaves under normal conditions. Now let's see the results that we got at LinkedIn when a server actually performs bad, how the algorithm behaves. So in this case, you can actually see 4 graphs here. The first 3 denote the latency seen on a server, and the last one denotes the QPS. And each servers are color coded here. I had to blur them out because they have our host names. In this case, the olive green server or the yellow server that you see here did see elevated latencies. And without our algorithm in place, the round robin approach basically sent equal queries to all these servers. At the same time, after we deployed this adaptive server selection feature, it so happened that there was a change in this cluster. There was a configuration management change where one of the servers was deployed with a lower JVM heap size. So all the queries that were sent to this olive green server started seeing elevated server processing times. And what we can see here is when the latencies are really high, the last graph, the QPS is significantly dialed down, right? And slowly as the server improves, we can also see that the QPS slowly improves and eventually converges when the server is back to normal. So this is a case of a prolonged server slowness. I also have another example for you of how it worked in production for a pretty eccentric case. So in this case, there was a nick flip issue in our production environment which caused erratic server latencies issues on multiple servers. And with round robin approach, we see that all the servers basically received equal load. But when we deployed server selection, you can see how quickly the algorithm reacts to various changes on the server. And eventually, when things are fine, the QPS converges. So let's talk some numbers here as to what kind of outcome we achieved at LinkedIn. So we have alerts set up in our production environment where every time one of the servers or one or more of the servers sees elevated latencies when compared to its peers, we have an alert that is fired. And either our SRE team or our dev team goes and looks at these alerts to triage them. So before this feature was deployed, we saw about 60 plus alerts every quarter. And after this feature was deployed, the alert count came down to 2. And these 2 alerts that you see here are genuine server slowness alerts that happened because of permanent failures like disk failures. And they actually had to be looked at. And translating this to the total number of engineering hours spent, the time has come down from 72 hours to just 8 hours per quarter. And ultimately, the goal of this feature is to prevent latency degradation when a server is not behaving well. In a system with a replication factor of 3, about 33% of the queries see poor latencies when a server grows bad. And the adaptive server selection feature helps improve that. And what we saw is we prevented latencies for queries for more than 90% of the cases with this feature deployed when a server becomes slow. And this is currently deployed in LinkedIn. We see the goodness of it, so we hope that you will use it as well and help us improve the feature. Thank you. Let's move on to the next part of the talk, which is query killing.
Cool. Thanks, Vivek. Really great feature. So as the second half of our resiliency story, I want to introduce to you how we are able to protect our servers and brokers from out-of-memory exceptions using automatic query killing at LinkedIn. So before we get into the details, let me show you why this is important. So as Vivek has already mentioned, we have a very large-scale deployment of Pinot within LinkedIn. With the scale comes the complexity. So the user can sometimes unintentionally run very expensive queries without prior notice. And they can also fire large data exploration queries. So all these queries can silently slow down a bunch of other queries before they trigger a worm, crash the server, and restart the server. This process can take as long as 10 minutes. So during which the user will face SLA breach and large-scale availability degradation. This is because currently the user don't get warnings for these expensive queries, and they may retry the queries for a couple of times. So this will bring down a few, if not all, replicas of a server. And what makes things worse is that these worm exceptions are very hard to triage and reproduce subsequently. Because we've lost all the context. And it can easily take our on-calls 4 hours to root cause just one worm exception by looking at the execution log and the heap dump. So here is a simple diagram of the scatter-gather query execution workflow of Pinot. As we can see here, when an expensive query is dispatched to the server, the worm exception can happen during the server segment processing. But even if luckily this query got through on the server, when the results are gathered and aggregated on a single broker, there is even larger chance of worm exception. So we will need to protect both our servers and our brokers from out-of-memory exceptions by killing the high-risk queries on the fly, by which we will need a generic framework that fits for both our broker and server. But there are certain challenges. The first one is that Pinot doesn't have per-query level memory allocation tracking currently. And it's not really easy to build that because, as we all know, Java has a pretty opaque memory management system with limited information exposed. And meanwhile, Pinot is a low latency, high throughput query processing engine. Therefore, we don't want to introduce a lot of overhead just because we want to track the memory. And last but not least, all the query execution on the brokers and servers are in multi-threaded environment. Specifically, we're using thread pools to do that. So it is also challenging for us to correctly gather and aggregate the usage stats from all these threads. But even with these difficulties, we are still able to stop more than 85% of the raw queries before they actually trigger worm exceptions. Let me show you how we are able to do so. So first, to kill a query, we need to make informed decisions. That is, we will need to kill the query with the expensive memory usage. So to do that, we need two pieces of information. First is that we'll need to know what queries are being executed on which thread in the thread pool. So let's take the Pinot server as an example. Here, when a query lands on the server, it will get dispatched with one query runner thread, which takes care of the main execution flow. Here, we set up an additional query execution status context, which basically records the query ID with a unique task ID unique to the thread. So here the query ID is Q1 and the task ID is 0 for this runner thread. And then when the runner thread dispatches the work, the segment processing to the worker thread pool, we will set up the context similarly. As we can see here, each worker thread has its own query ID and a distinct task ID. So all these will be linked together to form a tree-like structure so that we would easily track the hierarchical runtime context of these threads. On the other hand, we will also need to collect the usage stats from the threads. So each thread can report its own usage stats in the form of volatile primitives. For example, here, when we want to track the memory allocation, we can get the allocate bytes from the thread MX bin, and then we store it in the form of a volatile long. So the usage stats, it can be pretty generic, not limited to memory tracking, but also with CPU time, document scan during the query processing, and etc. So the reason why we want to do this is because all these query execution status and query resource usage stats, these collections are in the critical query path. Therefore, we want to use these volatile primitives to not take logs and reduce the overhead to the existing query execution code. Another advantage, before getting to the advantages, let's look into how we do this in a specific worker thread. So first, when the worker thread got dispatched with a query, we set up the query's task status. And then because Pinot's query execution is always written in an iterative way, therefore we can let each thread update its usage in each iteration. So by iterative way, I mean, for example, during the processing of a segment, we truncate the segment into a bunch of blocks. And each block will have like 10,000 documents, and we process them iteratively. So the thread will keep reporting its own resource usage stats until it finishes. Yeah, so another advantage of doing this is that this instrumentation to the existing query execution code is very easy to inject. So for example here, if we want to set up the query execution status for a worker thread, it only takes us three lines of code to inherit the context from the runner thread, set it up before the execution, and do the cleanup after the execution. For the resource usage stats, it's even simpler to instrument. So for each block, small block of data, we have a stack of operators running on top of that. And amongst all these operators, we only pick one common doc ID set operator and inject one line of instrumentation code, which will report the usage in every iteration. So all this make our change to the existing code very easy, and also make it very compatible for any future query execution code. So with the query execution status and the resource usage stats being correctly exposed, now we can, it will be easier for us to design the accounting task. We can model the accounting task as a time task, which is scheduled every few milliseconds. So every time it wakes up, it checks on the query execution status and the usage stats of each thread. After that, if we see an immediate risk of we aggregate the usage by query and terminate the query with the most usage. We do that by introducing a flag to the existing query execution code. So the code will check the query kill flag on each iteration. If it sees this flag set, it will terminate itself and return with error code. So the reason behind we're doing this is that Java doesn't provide us with a safe way of forcefully terminate a thread. And the accounting task is also intelligent enough to do the adaptive rescheduling, meaning that when we see a higher load on the server, we will reschedule the task more frequently so that we guarantee we kill the corporate queries in a timely manner. All right, let's dive deeper into the stats aggregation algorithm. So this part is a little more complicated, but I'll try to simplify it using a minimum example here by looking at only one thread. So the same logic will get applied to all other threads in the thread pool. So when a task wakes up, it will check on the status or execution status of a thread. So for example, for T1 here, we're having it running for the 4th task of query 3. And it will basically compare this status with the previous recorded status of the same thread. And we can see the status is actually different here, meaning that previously the same thread is running for query 2. And this happens because we're using a thread pool model, and the tasks can interleave on one thread for different queries. So what we do next is we will want to aggregate the stats of the finished task of query 2 to a partially finished query usage table. The reason behind we doing this is that although this task 1 of query 2 is already finished, there are still some other tasks running for query 2. As we can see here, the 4th task of query 2 is still running, meaning that the query 2 itself is not completely finished. In this case, the shared memory, the results, will not be deallocated. Therefore, we want to keep this piece of information. So after the finished query usage is being properly aggregated, we will then record the usage, the current query task status, and the usage stats for this T1 query. Sorry, for this T1 thread. And then the same logic will get applied to thread 2, thread 3, and so on. After we do this, if we see an immediate risk of we will then aggregate the recorded status, which is the tasks currently running, with the partially finished task usage to get the total usage of a query. Then what we can do is we can plug in some customized strategy. For example, we pick the one with the most memory usage and kill that query. So there are a few advantages of using this algorithm. First is that it handles both fixed and non-fixed thread pool, which is used on Pinot Server and Pinot Broker, respectively, so that we can use this one piece of code, one piece of logic to do the query killing on both our servers and brokers. And secondly, this piece of code, the aggregation algorithm, lives outside of the query execution path, which will incurs minimum overhead to the existing query processing. Thirdly, because this is a time task scheduled adaptively, we can view it as a sampling process. because it will only track the queries with large usage, but ignore the short-lived queries, which are not likely to trigger any exceptions. With this, we are able to limit the space and time complexity of our algorithm to a constant, which will not scale as we have more QPS. This is very important to us because we have very high QPS use cases within LinkedIn. And lastly, now with this framework, we can return the error message properly to the user so that the user will get informed and will retry the same query. OK, so finally, let's look at the benchmark and the results for the deployment of this query killing feature at LinkedIn. First, we did very exhaustive benchmark on the overhead of this feature. So here, basically, we're showing a CPU time benchmark for a prod high QPS use case. And as we can see here, the CPU time, CPU cycles goes into our new query killing code is only 0.3%. And out of which only half of it goes to the instrumentation code, meaning that the latency increase to the existing execution is minimum. And we also built an observability framework around our query killing feature, which we will get alerted when there's a query get killed. And then we can look at a centralized internal dashboard, which basically has all the kill queries, all the expensive queries with their usage, so that we can notify the users to update their query patterns timely. And lastly, as I have mentioned, we now can return the killing message to the user so that they can get informed. And we also identified the perf optimization opportunities during our rollout of this feature. We've actually found our deployment of G1 GC can sometimes be quite lazy in recycling the dereference objects on the heap. And this can cause heap usage to shoot up and long GC cycles, which will increase the tail percentile, like high percentile latency. Meanwhile, it will sometimes trigger false alerts and unnecessarily kill some queries. Therefore, we adopted Shenandoah GC, which gracefully solved these problems for us. And finally, let's talk about the numbers. And here, basically, before we deployed this feature, we can have up to 10 exceptions per quarter. But now, with this being rolled out, we can stop more than 85% of these raw queries and prevent the undesirable cascading effect for availability degradation, SLA breach. And also, the time used to triage these exceptions have also significantly reduced because now we have a holistic observability dashboard for the expensive and killed queries. And finally, we want to outline a few working items for the next step of our resiliency work. First, as we now have collected more stats for each query, we have the CPU time, we have memory usage, a lot of stuff. Now we want to build a fair query scheduler and some workload management inside Pinot, so that, for example, we can have resource isolation and query yielding, query scheduling based on user group usage. And secondly, also with the enriched stats, we can do some early rejection of queries, meaning that we can filter out some really raw query patterns before they even land on our broker. And with query killing, we want to make it more efficient by propagating the killing decision from one server to others so that the query killed on one server will not continue to execute on other servers. And for adaptive server selection, we want to incorporate like more enriched stats from the servers, like CPU load, memory load, to make the algorithm even more robust. And we really look forward to this resiliency feature being used and improved by the open source community. Thank you.
If there are any questions, we can take them.
Yeah, on the query killing capability, how do you think about that from a user messaging consistency perspective? What I'm getting at here is sometimes the server is lightly loaded and that query could run successfully. Other times it's contending with a lot of other users and that query cannot. Do we kill it all the time? Do we kill it some of the time and let it survive others? And how do users think about that when they're like, the query ran fine yesterday, it doesn't run fine today?
Okay, so basically you're asking what would the user think if the query is like successful running when the server load is low, but when the server load is high, the query might get killed, right? So yeah, I think it's definitely a very important experience issue from the user. So right now, the query killing feature is here to protect us from a lot of unexpected raw queries, which one query can cause the exception on a server, like solely. And meanwhile, like sometimes the user fires the query, it can bring down a bunch of queries. But for these queries, we have a herd of big queries. These, as we mentioned, we want to have some fair scheduling and query admission control, where we really, based on the stats, we can do rate limiting, so that they can like fail fast and return a message to the user, seeing that we don't have enough capability on the server. Does that answer your question?
Yeah, I think I get it. I don't think that comes up to things like Tableau very well, but yeah, it's interesting.
Cool.
All right, so I might have missed it because I couldn't read the screen for you, but at some point you had this question in your decision tree, which was OM risk. Sorry, what's in that? What's the decision you make there? Because you need to know how much memory is allocated to the system, how many threads you can run. So is it just based on how much you expect each thread to take the max amount? It was a little, yeah, what's the OM risk decision there?
Oh yeah, that is a great question. So this out-of-memory risk is tracked during the runtime by querying the Java's interface for the heap usage. And then we can set a static threshold there by saying that when the total heap usage goes beyond a point, we start to kill the most expensive query. We don't really aggregate all the usage of every query and figure out this value. This can be directly retrieved from JVM.
And how quickly do you make that decision of killing? So for example, you kill one, you look at the heap again, and you immediately keep killing, or you give some time?
Yeah, that's a good point. So you're asking, like, what do we do after we kill one query? Do we give some grace period? Yes, we definitely give some grace period. Actually, we give time for the GC to kick in, to deallocate that part of memory. Otherwise, we will need to continue killing, like unnecessarily kill a lot of queries.
Let's thank our speakers.